Morning, you guys. How we doing this morning? Doing okay? Yeah. Hey, thanks to y'all that came out to see Rebecca's talk yesterday. I hope it was useful. I know it can feel sort of, y'all had more people experience, you probably understood more than I did, but you can feel sort of reeling from when you see an academic talk like that. But, as you go to conferences and as you read their papers, like she was talking about, that you really become to sort of understand the vocabulary and the sort of how people speak about their work in that way, and it just begins to make more sense. I thought she was a really good speaker, actually. She did a good job. I want to point out to you that we do have an exam coming up. Today we're on the 22nd, and so we have Friday, and then next week is Mardi Gras, so we'll have that week mostly off, but we'll come back on Friday, and then that following Monday we'll have our exam. So keep that in mind. We'll go over, where did we leave off last time? I think we have gravitational fields, the fluxes and the fields, and then all of chapter 2 on potential, electric potential. It's a lot of the same stuff that we've seen, but electric potential. And then we'll see this chapter on capacitors in full. We'll finish it either today or we might go a little bit into next Friday. Or wait, let me see. No, we'll finish it actually because we have 2 classes this week, so we'll definitely finish chapter 3, or chapter 2 rather, and we might get a little bit into chapter 3. But everybody in the lab here? Who's not in the lab? Some of y'all just not okay. Well, we might get a little bit into chapter 3. We'll see. Chapter 3 is very short. All right, so let's pick up where we were last time with this capacitor circuit. You can see one like this on the exam, though I'll show you one that's more like what you'll have on the exam. But this one's good practice. So remember, we first wanted to find the equivalent capacitance, and so to do so, we first said this is the smallest part that's either in series or parallel. A 2 and a 2 in series, 1 over a half plus a half is equal to 1. And then I like to redraw my circuit. It really helps me to sort of think about how the voltages and the charges are distributed. So I redraw it here. I find the equivalent of this. 1 plus 3 plus 7 is 11. And then I find the equivalent of these two. 1 over 1 plus 1 over 11 is equal to 0.92. So now the question is asking, what is the potential difference across the 3 microfarad capacitor? So let me just sort of say in words what we're going to do, and then we'll do it with the numbers. My first thing I want to do is find the charge on this capacitor. Because I know capacitors in series have the same charge. They also have the same charge as their equivalent capacitor. So whatever charge I have here, I also have here, and I have here. And once I know the charge on each of these 2 capacitors, I can find their voltage. Because if you know any 2 quantities, you can find the third quantity. So when I get the charge on this capacitor, I can also find its voltage. And then I'm almost done. Because let's see, what am I looking for? The 3 microfarad? Once I know this voltage, I know that it's the same voltage here, here, and here. Because those 3 are in parallel. So let's do it. First, we're going to find our charge on this equivalent capacitor. That Q is equal to C times V. That's going to be 0.92 microfarads times 10 volts, or 9.2 microcoulombs. So that means I have 9.2 microcoulombs here and 9.2 microcoulombs here. So now I can find my voltage. V is equal to Q divided by C, which is going to be 9.2 over 11. And that is 0.84 volts. Notice that the big capacitor has the small voltage, 0.84. And by the way, I don't have to go through this to find the voltage here. I just say it's 9.16. How did I get that? Subtract it from 10, right? Because I know that these 2 have to add up to equal to the 10 volts that I have here. So I have 0.84 volts. And so my answer then, actually, we can go and write down all the voltages here. I know that I have 0.84 volts here, and here I have 9.16 volts here. And then on these 2 microfarad capacitors, I have, well gosh, what do I have on that 2 microfarad capacitor? Is it 0.84? No, it's what? Not everybody at once. I have these two capacitors in series. Remember, when you have capacitors in series, their voltages have to add up to the total capacitor, the total voltage. And since these two are identical, they're going to have the same voltage. So I'll have how many volts across? I have 0.42, which is 0.84 divided by 2. So I have 0.42 volts here. 0.42 volts here, 0.84, 0.84, 9.16 volts. And once you know two of the quantities, if I asked you what is the charge, you can find the charge, just do Q equals CV. So you'll have a similar circuit to that, except it's going to be laid out a little differently. So part of the hurdle will just being able to draw the circuit in this way, because we'll sort of draw it on more of a grid-like pattern. All right, we'll do a couple more of these. Okay, so if you haven't gotten it yet, that's okay. Tell me, what is the equivalent capacitance of this circuit? It's okay to use your calculator, but try to look at it, not use your calculator. Think about the numbers that we use. Alright, let's try to wrap it up about 15 seconds or so. Stop at 2 minutes. Stop at 2 minutes. It's 5 more seconds. Alright, 2 minutes. Alright, let's see. A is right. Eventually you'll be able to look at these combinations of capacitors and not really have to think about it very much. You'll say 2 and a 2 in series, well, that's equivalent to a 1 microfarad. 1 over a half plus a half, that is equal to 1. And then a 1 and a 3 in parallel, well, that's just 1 plus 3, so that's 4. And then this whole thing right here is 4 microfarads. It's in series with 4 microfarads, and 1 over a quarter plus a quarter, that's equal to 2. So let me write that out. Here I have 1 over a half plus a half, that's equal to 1. And then I combine this, I get 1 plus 3 equals 4. And then I'm left with 2 4 microfarad capacitors. So I have 1 over a quarter plus a quarter equals to 2. So A is the right answer, that it's equal to 2 microfarads. Again, with practice, you'll begin to see these patterns, and you'll be able to see sort of how the capacitors fit together. But it really takes practice, and then you just begin to see the patterns come out. Let's look at this circuit. This one is laid out a little differently than the ones that we've been doing, but I guarantee you that it's very similar. If I draw it in a different way, you'll say, oh, that circuit's easy. But usually when you see circuit diagrams, they try to make circuit diagrams as compact as possible, because you often have hundreds of different devices that are at play in a circuit, and you don't want to put it on a big poster, so they sort of make them more compact. And they don't draw them the way that we've been drawing them. They'll draw them more like this. When you're tracing out the flow of electricity, or in this case, the way that the capacitors are laid out, I always like to start at the big side of the battery. And then I just sort of trace my way through, and I look for junctions. So like, for example, there's my first junction. And then I start to redraw it. I'm going to redraw it like this. I have my 12-volt battery. I have my 6 microfarad capacitor. And then I come to a junction. And at that junction, I split into 2 pieces. I have one piece that goes up in this direction, and one piece that goes in that direction. So 2 branches right there at that junction. And then I have no other junctions in each of those branches until I get to the next capacitor. So I'm just going to go ahead and draw these 2 capacitors, C2 and C3. So I have, I'll put C2 up here. That's my 4 microfarad capacitor. And then down here, I have C3. That's my 1 microfarad capacitor. I'm at 12 volts here. Now, once I get past C3, if I go through here, I have a clear path back to the battery. And you might say, well, what about these junctions and stuff? Well, I'm not really concerned with those, because from here, I can go straight back to the battery. And honestly, my electrons, they just want to get back to the battery. So they'll go straight through here and go back to the battery. So let's just sort of leave that for a moment. Let's go back and look at C2. As I go through C2, I come to another junction. That means that I'm going to have another embedded parallel branch up here that has 2 parts to it. So I can draw a 2 microfarad and a 2 microfarad. This one is 2 microfarads and 2 microfarads. And once I come through those, this junction comes back together. I'm going to go ahead and close off this, and there are no other elements there. And then everything goes back to the battery. So I can draw this like this. These are the same circuits. And you might look at this and say, well, that doesn't really look the same, but it is. And we can map out the circuit looking for the junctions in the circuit along the way. And we'll see that it is, there are identical circuits. And now from here, you can probably think about what is the equivalent capacitance. So we're 2 and 2 in parallel. What is that equal to? 4, right? 2 plus 2 is 4. And that gives me a 4 and 4 in series. Now let's see, we've heard that number before. That's a 1 over a quarter plus a quarter. That's 1 over a half. That's equal to 2. All right, so this whole part up here is 2 microfarads. And then I have down here a 1 microfarad and a 2 microfarad in parallel, so that is 3. 2 plus 1 is 3. And then I have a 3 and a 6 microfarad in series, and that's going to be 2. Let me write that down. So first, I recognize that this is not 1 over, it's equal to 2 plus 2, which is 4. And then I'm going to redraw the circuit. And this gets a little tedious, and you might find that, you don't need to go through all these steps, but for now I'm going to do it. That's 6, 4, 4, 1. Now I'm going to combine these 2 capacitors, 1 over a quarter plus a quarter, that's equal to 2. I'll redraw it again. That's going to be 2 microfarads, 1 microfarad, 6 microfarads. And then this part becomes 3. Redraw it again. And it's left with a 6 and a 3. 12 volts. And then finally, a 6 and a 3. That's 1 over 6 plus a third is equal to 2 microfarads. Now at this point, we've worked these, so we want to step back and find, what was I asking? I think the charge and the voltage on each one. Yeah, the charge and voltage on each capacitor. The process here, I'm going to show you a couple different ways. I know my charge here, Q equals CV, is 24 microcoulombs. So that means I have 24 microcoulombs here and 24 microcoulombs here. Because capacitors in series have the same charge. Capacitors in series have the same charge. Remember, it's an induced charge that's set up, and they distribute that entire charge throughout the entire series of capacitors. Now we can find the voltage. Voltage is Q over C. So we have 24 over 6 is 4 volts, 24 over 3 is 8 volts. But look at the capacitors and how they're distributed. The voltages. Does a small capacitor carry a big voltage or a small voltage? Think about it. So I have Q equals CV. If C is small, what happens to V? Does it go down or up? It goes up. There's an inverse relationship between C and V given QV constant. So if C is small, V is big. So I have my smaller capacitor, I have a bigger voltage than my bigger capacitor, right? And by a factor of 2. And since those numbers have to add up to equal to 12, then I know that the smaller capacitor will have 8 volts, and my bigger capacitor will have 4 volts. They'll be different by a factor of 2, and they have to add up to equal to 12. All right? So now I got some information here. I know that I got 4 volts here. I know that I have 8 volts here and 8 volts there because they're in parallel. Capacitors in parallel have the same, what, charge or voltage? Voltage, right. So that'll be the same for resistors, which is good, but capacitors in parallel have the same voltage. Can carry that over here. I got 8 volts, 4 volts. This is microcoulombs. Not microcoulombs, sorry, microfarads. Eight volts, 8 volts. I have 8 volts across this 2 microfarad equivalent. And since these are 2 identical capacitors, what's going to be the voltage across them? 4 each. So each of them will split that 8 volts. So I'm going to have, let's see, I'll just use these 4s. No, let's see, these are 4 microfarads, but they also have 4 volts across each of them. And we're almost done. I have 4 volts here. I also have 4 volts here and 4 volts here. So now I can write down all of the voltages I have on this entire circuit. On the 6 microfarad, I have 4 volts. On the 1 microfarad, that's right here, I have 8 volts. On C2, which is this capacitor, I have 4 volts. And then C4 and C5, which are these 2 capacitors, I have 4 volts each. And then the charge is just the C times V for each of those. So for example, C1 will have 24 microcoulombs, C2 will have 16 microcoulombs, C4 will have 8, C5 will have 8, and C3 will have 8 microcoulombs. Q equals C. Alright? Your test problem will be similar to that. Maybe 1 or 2 more capacitors, but very similar to that. Look back at all the old tests. All of them have a capacitor question like this. So take a look at those, and they'll give you good practice. There's some in your homework as well. Well, let's do another one. I think I have another one in your workbook. Actually, let's do these. There are a couple clicker questions, and then we'll come back to a more complicated circuit. Consider this circuit. What is the charge on a 3 microfarad capacitor? What is the charge on this capacitor? Now you'll need to know the voltage. Well, there are a couple of ways you can do this. The easiest way is probably to look at it and think about how the voltages are distributed across those different capacitors. And once you find the voltage, the charge is C times V. That's the charge. If you finish that one, go on and do the equivalent on the next one. Many of you have the right answer, a couple of you do not. Feel free to ask your neighbor. All right, let's stop. Just a few seconds. I'll stop at 238. 238. Okay, good. B is right. Easy way to do this is to think about how the voltages are distributed. Smaller capacitor, bigger voltage, 8 volts. I know it has to be 8 because it has to be twice this voltage, and they have to add up equal to 12. So for example, if this was 24, it would be 16 and 8 volts. So if 8 volts, 3 microfarads, 24 microcoulombs. Or another way to do this is to figure out what is the equivalent capacitance. The equivalent is equal to 2 microfarads, and then the charge on that equivalent capacitance will equal to 2 times 12, because that's the voltage, 12 volts, which is also 24 microcoulombs. All right? See, I don't have a joke, but I just have some sort of general advice for you. You ever get cold in this room? Sometimes cold. It's fairly comfortable in this room now. If you ever get cold, you have my permission. You can just come and stand, because this is like the warmest part of the room right here. This area is the warmest part of the room. Sometimes I get cold, but other times stand over here. It's like 90 degrees over here. Isn't that one too? Yeah, that's right here. Like 180 degrees over here. That really was a joke, like that wasn't advice. I don't know if y'all got it, but it was a joke. All right, what's the equivalent capacitance of this circuit? Try to do it, just look at it, just try to look at it and tell me what is the equivalent. let's stop at 50. Stop at 50. Let's guess if you're not sure, ask your neighbor. Many of you have the right answer. All right, A is right. So to do this, I start here. The equivalent of this is 2. 2 plus 2 is 4. And then I have a 4 and a 4 in series. And the equivalent of 4 and 4 in series is 1 over a quarter plus a quarter, which is 2. And then let's go ahead and do this next one. What is the potential across the 2 microfarad capacitor? So that is across the potential across this capacitor. Again, try to just think about how the voltages are distributed across that circuit. Looking great. Y'all doing a great job. I think y'all are getting this. The hard part on these capacitor circuits is that being able to map out the circuit and take that funky grid-like pattern and translate it into something that you know looks more like what it is. All right, let's stop at 40. Just a few more seconds. Oh, well, I thought y'all were getting it. Let's see, so C is right. So if I want to know the potential across the 2 microfarad capacitor, let me redraw this circuit. My 4 microfarad, those 2 4s became a 2 microfarad. That's the equivalent of these two. And then I have another 2 microfarad. And then I can redraw it still. I get a 4 and a 4. And then this is 12 volts. These two are in series. Sometimes you get confused because you got this bend, but notice there are no junctions here. I just have a bend in the circuit. If it makes you feel better, you can draw this capacitor up here and be the same thing. So I have 12 volts here, so that means I have 6 and 6 volts here and here. Because they're identical capacitors, I can just split up that voltage equally. And I don't have to do anything funky like find the equivalent or find the charge or any of that business. And since this is 6 volts, that tells me I have 6 volts here and here. And so that's the answer. I want to know the voltage across that 2 microfarad capacitor is 6 volts. All right. You might see some multiple choice questions like this that are, you know, I don't usually like to do a lot of calculations on a multiple choice, but I don't really consider these to be calculations per se, as sort of thinking about how the voltages are distributed across these circuits. But also in your free response, I'll try to make the numbers as easy as possible so that you don't have to go through a whole lot of calculations to get to the answer. That if you can map out the circuit the way it, you know, the way it looks, sort of more like in this pattern, then you'll be able to see how those voltages are distributed. Let's look at this old test question. And again, online there's a bunch of different ones so that they're good for you to practice. And it'll be worth, you know, 15 points, so it's not insubstantial. Okay, yeah, so on this one, the tricky part comes about right here. Because you probably see that as I go along that I get a parallel branch right here that has 2 parts to it. But then that parallel branch right here, it closes. And in fact, I can take this point. If I don't have any electrical devices, I can just sort of get rid of wires. So I can just sort of collapse this down to a point and then open up a new parallel branch. So what you're dealing with here are 2 parallel branches. You have one right here, and then it closes, and then you have another one right here, and it opens back up into another parallel branch. So take a minute and try to sketch out what you think the circuit looks like. In about a minute or so, I'll show you what it looks like. And once you get that, I mean, the problem is largely done. I'm going to start drawing the circuit up here. Alright, so this is C2 and C4. C2 equals 3, C4 equals 6, and C3 equals 1. And then I have C6 and 7. And C5 is 2. Let's take a look at that circuit for a moment and see. Don't just sort of look at it. Think about what is the equivalent capacitance. Can you tell me what is the equivalent capacitance? So I got a 3 microfarad here. It's in series with 2 other capacitors. I see some familiar combinations here, the 3 and the 6, and the 2 and the 2. What is the equivalent capacitance of that? Well, the 3 and the 6 is what? 1 over a third plus a 6 is 2, right? 2 and 1 is 3. The 2 and the 2 is 1. With the 2 is 3. Okay? So I have a 3, I have a 3, and a 3. If I do a 3, 3, and 3 in series, what does that give me? It gives me 1, right? No, 1. I have 1 over a third plus a third plus a third, which is 1. 1 over 1, which is 1. So let's redraw this circuit a little bit. But, we know where we're headed. Like, I can tell you right off, just knowing that look, I got 4 volts here. Likewise, I got 4 volts here, and I got 4 volts here. Well, shoot, we can almost answer the whole question. I got 2 volts here and 2 volts here. You'll see how I did that? Once I know that I have 3 identical capacitors that are all in series, I know they share the voltage the same. So I have 12 volts here. So I have 3 volts across this, 3 volts across this, excuse me, not 3 volts, 4 volts across this, 4 volts across this. I got 4 volts across those 3 different parts of the circuit which are identical. Because these are in parallel, I have to have 4 volts here and 4 volts here. I have 4 volts across these 2 capacitors, but they split it up because they're identical into 2 and 2. Now this one's a little bit more complicated because it's not an even number, but I know that across these 2 capacitors I have 4 volts. One of them is going to be twice that of the other, and they have to add up to equal to 4. Let's see, the equivalent is 2 microfarads with 4 volts. That means I have 8 microcoulombs here and 8 microcoulombs here. So my voltage will be V is Q over C. My voltage will be 8/3 volts and 4/3 volts. So I had to do a little extra step there where I had to figure out the charge because I can't really do those fractions in my head, or maybe you can. But I have 8/3 on the small capacitor, and then half that, or 4/3 on the bigger capacitor. Okay? Let me step through. This would be the answer to the question. Like, you could just stop at that point. But let's step through and do it a little more rigorously in case you're still sort of struggling with it. So I have 12 volts, 3 microfarads. This is 2 microfarads, 1 microfarad. I'm just stepping through and finding the equivalent. That's 1 microfarad, 2 microfarads, and then recognize that both of those are 2 plus 1, so I'm left with 12 volts, 3, 3, and 3 microfarads. All right. Because these are all identical, I can just sort of stop here and say, well, gosh, this has to be 4 volts, and 4 volts. If those are all 4 volts, that means I have 4 volts here and 4 volts here because they're in parallel. 4 volts here and 4 volts here because those are in parallel as well. And I've already determined that this is 4 volts. And then I can step back, as I said before. And some of these just translate directly over here, here. But if I have 4 volts on this capacitor, these two split it up into 2 and 2 volts. And then on this one, so it's already done, let me do it again. I say, well, that one has 8 microcoulombs. Q is equal to C times V, which is equal to 8 microcoulombs. So I have 8 microcoulombs here and 8 microcoulombs here, allowing me to find the voltage. So you see, circuits are really just sort of like a little puzzle you have to put together and figure out how all the pieces fit. You can go back and check things, like you can say, well, I know that my sum of all my potentials has to equal to this. I got it split in some cases equally. I got it split in some cases unequally. Sometimes my capacitors share the same voltage if they're in parallel. And once you get those rules, capacitors in series have the same charge. Capacitors in series, the equivalent is that 1 over business. Q equals CV, and for capacitors in series, all the voltages are the sum of the individual voltages. And then the rules for the parallel, capacitors in parallel have the same, what? Capacitors in parallel have the same, it's either charge or voltage, which is a voltage. The equivalent is the sum, Q equals CV, and then that's really it for capacitors in parallel. Once you know those rules, which we've laid out before, working these circuits is, I wouldn't say it's easy, but it's certainly doable. All right. It'll help you with the resistor circuits, which aren't going to be on this test, but we'll see it on the next test because they'll work similarly. Let's do a few clicker questions, then we'll come back to this energy business. Where did we leave off on this chapter 2? By the way, softball is playing tonight. I think their game is at 4 or 5, but they've been on a tear, so I think they'll probably have a pretty good game tonight. They're doing really well. Y'all know they're having a doubleheader. I think it's at 4 and 6. There's no admission. Usually fun games. Did we do these? Can somebody tell me where we left off? Does anybody know? Anybody? Y'all don't know? 2.2. Oh, we didn't do. Oh, we did these, didn't we? Oh shoot! I'm sorry, I'm giving you all the answers, huh? All right, I'm sorry. Let me. What's going? Are you serious? We didn't do any of these? Is that right? I guess we're not been. My other class has been tested on this already. Okay, well, shoot. I'm sorry. Let's try these. Alright, so remember, this will be good review anyway. So, we have these configurations of charges. We want to bring them together. Ask how much work is required to bring them together. The amount of work that's required to bring them together is equal to the potential energy of the charges. So remember our potential energy, U, is equal to KQQ over R. We saw this very similar thing for gravitational potential energy, but our electric potential energy is KQQ over R. So when you have these configurations of charges, you want to consider each distinct pair of charges. We've done it for masses, we've done it for charges too. But which of these configurations requires more work to bring together, or has the most potential energy in their electronic configuration? let's stop at 133. 133. Okay, good. B is right. Remember, you have to consider each individual configuration of charges. Let me just go to the next slide. Add it over all the pairs. So if I do this one, it's K11 over D, and then I do that 3 times, and I get 3K over D. So that's sort of the total potential energy, because I have 3 sets of pairs. Whereas this one is just going to be K times 2 times 1 over D, which will be 2K over D. You'll probably have a calculation problem regarding either gravitational potential energy. Should we do that yet? Yeah, that's chapter 1.5. Or, no, that was chapter 0.5, excuse me. You'll probably see electric potential energy, which we've seen before. Let's see. Where at this point is the electric potential equal to, or what is the electric potential at point A? What you have here is a plus 50 microcoulomb charge and a minus 50 microcoulomb charge. I want to know at point A, is my potential bigger than 0, equal to 0, or less than 0? Remember, potential is a scalar quantity. Though you can have negative potentials, it doesn't have anything to do with direction. It only has to do with sort of the relative energy of the place. So what is, because of these two charges, what is the potential at point A? Is it positive, 0, or negative? All right, let's stop at minute 5. Minute 5. All right, good. A is right. It's going to be bigger than 0. The reason it's bigger than 0 is because I'm closer to the positive charge. So the positive charge sort of dominates the potential. I'm further away from the negative charge. The negative charge also gives me a negative potential, but since I'm further away from it, that it's the negative influence is less than the positive influence. What is the electric potential at point B? The electric potential at point B. All right, point B is a point equidistant from both charges. One is positive 50, one is minus 50 microcoulombs. Let's stop at 30. I'm going to stop at 30, just a couple more seconds. Okay, very good. B is right. So at that point, the potential here is equal to KQ over R plus K negative Q over R. So those add up to equal to 0. All right. We went to that new bank. You ever know that new Capital One bank they have on Canal? And it's fancy. It's like they got big TVs, but they don't have the little paper slips for deposits anymore. You have to do it on a tablet or whatever. But anyway, that's not the point. We went to the bank because we were having some issues with our balance, like in our checkbook. And so I went up to the cashier and I asked her, I said, could you just check our balance? We're having some issues. She pushed me. Again, not a true story. That was a joke if you didn't get it. 4-point charges are arranged at the corners of a square. Find the electric field E and the potential V at the center of the square. So remember electric field back from the previous chapter. The electric field, I imagine a positive point charge here, and I ask myself the direction of the force due to the other charges. So for example, if I'm considering this charge, the electric field would be in that direction. So you go around and ask yourself what the electric field is, and then add up the vectors. No electric field on this. All right, let's stop at a minute 5. Minute 5. Okay, so we're sort of all over the board. So let's see what the electric field is. The electric field due to this charge is in this direction. The electric field due to this charge is in this direction, and due to this charge is in this direction. So the net electric field is in this direction. So I can get rid of C and D. I can get rid of these two. So either the potential is 0 or the potential is not 0. Which is it? I'm sorry, I can't get rid of those. I get rid of A and B. Sorry about that. So see, my electric field is not 0, and the potential, on the other hand, is 0. So D is the right answer. Why is the potential 0? Well, look, I'm equidistant from negative and positive charges. So the potential due to this charge cancels with the potential due to this charge. And then vice versa are also true for these. The potentials all cancel out. By the way, I was talking to Rebecca yesterday, our speaker, and she said that, she's sort of gone into physical chemistry a little bit, as well as some other areas of chemistry, but she said that, the basics of physics comes up a lot, and so that, like, this course in particular is helpful in just helping her to move forward as she studied this electron transfer. So, it seems a little esoteric to talk about potentials and fields and all this business, but it's quite important, especially as you move into graduate school, into upper levels of chemistry, because, you deal a lot with charges. That's what you do. And so it's important to understand how charges interact with one another. All right, so at which point does V equal 0? Let your 1s be A's, 2 be B, 3 be C. All right, let's stop at 23. 23. Okay, good. E is right. The electric potential is 0 at all points, because all points are equidistant from equally but oppositely charged objects. Okay, this one's similar but a little bit different. I have these configurations, and which of these give me a potential equal to 0 at all points on the x-axis? So as I move along the x-axis, is the potential always 0 on those points due to these configurations of charges? And really what you're asking yourself is, on that x-axis, are you equidistant from equally but oppositely charged objects? You have to be equidistant at all points along that x-axis. All right, let's stop at 110. 110. Okay, good. A is right. Look, at A, here, I'm right here. Notice I'm equidistant from those two charges, so their potentials cancel out. And here they cancel out as well. So, for example, the potential at this point, if this is R, is going to be K times plus 2 over R plus K times minus 2 over R, and that's equal to 0. And in a similar way, these two voltages will cancel out as well, because I have equal but opposite charges. But if you look at the other ones, they don't do that. So right here, I'm close to that, but I'm far away from that. So my potential is going to be more positive than it is negative due to those charges. Now there is one point where V equals 0, and that's right there, where I'm right on the middle of the x-axis. And a similar thing over here. Notice these distances are different, so their potential doesn't cancel out. All right, how about on the y-axis? So now we're looking at y-axes in this direction. In between those two charges, those four charges. Looking at the y-axis now instead of the x. All right, let's stop at 32. 32. Very good. That's C is the right answer. Notice that at C, I'm equidistant from these equal but oppositely charged objects. All right. Did I ever tell y'all I used to be a bartender? Ever tell y'all this? I did tell you? Maybe. Yeah, I worked at this restaurant. It's kind of like Flanagan, so it was a fairly nice restaurant. And I waited tables, but then I started bartending. Good money in bartending, but terrible hours for a student. I know some of you work as servers, right? Still work? Yeah, terrible hours, so I don't really recommend it. But anyway, it's okay. I understand. But anyway, one night I was at the bar, and this guy walks in, and he was sort of stumbling. Like, he'd obviously been drinking a little too much. And the strange thing is, he had jumper cables, like around his neck. And I didn't know what the deal was. But I told him, I said, look, you can come in, but you better not start anything. Once again, not a true story. Like, that was a joke. All right, I did 10 bar, but that was a joke. Let's see. Can y'all see those lines? I think they come out in your workbook. Which 2 points have the same potential? A and C, B and E, B and D, C and E. Or is there no pair of points that have the same potential? They come out okay in your workbook. All right. We'll stop at 32. 32. Okay, good. D is the right answer. Let's see, I have one joke, and I'll let y'all go. Y'all know I wanted to be an English major in college. I really did. I was going to be an English major, flat out. I loved English. Loved writing. So, I like this joke. What is the difference between a cat and a complex sentence? Never thought about that, have you? A cat has claws at the end of its paws, but a complex sentence has a pause at the end of its clause. All right? Y'all have a great day. Listen, I don't think we're going to have Chapter 3 in the test at all, but we'll probably get into Chapter 3 a little bit before the test. And then we'll finish up these clicker questions. We have one more topic to finish. Y'all have a great day.